Hello everyone. In this session, I want to talk about the neural networks. So initially we will spend some time discussing the conceptual aspects of neural networks, and after that we'll take an example data set and try to apply the neural networks for that particular data set, do the necessary interpretations from the data set, right? So that is how we will go ahead. But let me tell you here with a word of caution in the beginning itself that neural networks is a kind of very complicated, complex kind of a topic, right? And it is based on various mathematical transformations. So the conceptual aspect of it in general is much heavy in case you don't have a proper background in mathematics. But at the same time, because of various technologies like R, we can directly use these neural networks for our business prediction purposes. So as an applied user of neural networks, I can comfortably use them for prediction purposes or for classification purposes. So I can very well use the concept of neural networks because tools are doing the job for me. But if I have to get the mathematics behind it, then probably I need to have so many concepts in mathematics clear. So here the focus is just to give you a broad outline of those mathematical concepts, with the major focus being how are these neural networks actually used for the prediction purposes. So that's the major objective here. So probably you can say that we would treat neural networks majorly as a black box, while some amount of basic understanding would be provided, but still as a black box for executing a business solution for a prediction problem. So that is how I am going to look at the neural networks per se. So initially we will talk about why to use neural networks, when to use neural networks, what are neural networks, etc. Then we would try to link in the concept of artificial neural network. How does it work? And some of the major components of this artificial neural network, wherein we have to understand what is this activation function, what are the different types of activation functions are there, and how does my prediction change with the change in the activation function. So we can understand all these aspects out here. Then how are the neural networks typically built? So the architecture of the network, otherwise we call as the topology. How many layers are there as a part of this network? What goes into what layer? So we are spending some time in terms of understanding the network topology. Then how do we really train the neural networks? We talk about a process called backpropagation. So using this backpropagation, how do I really train the neural networks? So these are some of the conceptual aspects that we are going to work out with before going ahead in terms of taking up an example data set and implementing neural networks on that data set, using that for the prediction purpose. So here I wanted to bring in something more. We will take one single data set, right? We will try to do, so this data set, the objective is numerical prediction. So we'll try to, we know that we can use regression models for doing that numerical prediction, or we can very well go with regression trees, we can go with model trees, or now we can even look at neural networks. And probably in the next session I'm going to bring in the support vector machines. Even the support vector machines can be used for predicting a numerical data. So what I really want to do is I'll take a data set quickly I'll try to execute these three which we have already dealt earlier with the same data set, and we would also do the neural networks on the same data set. Try to see how each one of them are really improvising the solution for this particular data set, which solution looks more and more appropriate, etc. Right? So that's what I want to see, and probably when I'm discussing the next session on support vector machine, I want to take the same data set and I want to extend the example as well. Alright, so let's get started. So what is typically seen is neural networks is one of the most powerful machine learning algorithms in the today's world, because the applications of this neural networks, they are across several domains. I can use them in finance, I can use them in behavioral sciences, I can use them in humanities. There are wide varieties of areas. In science, I can use a lot of neural networks. So there are applications in many domains across different kinds of tasks. So that's one of the main reasons I can really vote for neural networks as the most powerful kind of a machine learning algorithm. But it's primarily a black box. Very, very difficult for me to understand the way the model is getting constructed. The workings of that model are very, very difficult to understand. The calculations what are typically done as a part of the neural networks are very, very difficult to understand. So if you try to understand the mathematics, it is a very, very complex mathematics. So unless I have a very good hold in mathematics, the advanced mathematical concepts, I cannot really understand the calculations of neural networks. But functionality wise, business wise, whenever we are using the word a neural network or otherwise artificial neural network in detail, we are again modeling a relationship between an output, generally which is a dependent variable, and a set of independent variables which are typically called as inputs. So here we use the word signals. Output signal is more like a dependent variable, and we are trying to build relationships between a set of input signals, which is a set of input variables, and one output variable, which is a dependent variable. So more or less we have seen regression also does the same purpose. Regression tree also accomplishes the same. Model tree is also designed for the same purpose. So you could see here building the relationships. So even the classification models, even they do the same. We are trying to build relationships between output and a set of inputs. So all these come under the supervised learning processes. In short, if I have to put, these all are a part of the supervised learning processes itself. So when it comes to neural networks, they are very, very versatile learners. Almost any kind of a learning task can be accomplished through neural networks. So if you see till now, whatever the various sessions that I have dealt, in the supervisory learning, we said two broad forms. One is classification models, one is numerical prediction. Under the numerical prediction, till now we have looked at these three: regression trees, model trees, etc. Under the classification, we talked about nearest neighbors, right, naive Bayes, and we also looked at decision tree, classification rules. These all come under the classification model. These all come under the numerical prediction model. But the neural networks, I can put them into either of them. And in some cases, I can use neural networks for unsupervised also. These are one such kind of technique which are typically used both for supervised as well as unsupervised kind of learning processes. So that's one more advantage associated with the neural networks. So when the relationships between the input and the output are very, very complex, I can very well think of using the neural networks for modeling the relationships between the inputs and the outputs. So that's the basic background behind the neural networks. Now coming to the basic concept of the neural networks. So basically it's a diagram. If we are talking about any kind of a network diagram, so we are trying to link or put a relationship between different inputs, right? In general also, we are talking of different inputs, mapping it to a particular output. So we have several input variables in this diagram. I have three input variables x1, x2, x3, and I have an output variable y, right? So when I'm talking about a network diagram, I'm trying to build relationship between x1, x2, x3, which are the input variables, and an output variable which is y. You also see here I'm giving some kind of weights w1, w2, w3 to each of the input variables, right? The reason why I am giving the weights is, even if you look at the human being, human brain trying to understand any particular input information, I try to give some weight to some information, I try to give very less weight to some other information. So that's the same way, different inputs that are being supplied to it, they are carrying different kinds of weights. So if I am having three different inputs, three different weights are being assigned to them. So some of them will contribute more to the overall information, some of them will contribute lesser. But right now there is again a mechanism which the system will use to determine W1, W2, W3. But for now you just try to understand that there are different weights that are associated with different inputs. And so which means to this, at this stage, the information that comes out is W1x1, W2x2, W3x3. Now this particular signal that is coming, W1x1, W2x2, W3x3 signal, is passed to what is called as an activation function. So this is what we are calling as an activation function. So we are not getting the inputs directly here. We are getting the weighted sum of the various inputs. So that inputs that are coming, so that input is what we are calling as an input signal, which is a weighted input signal. So the activation function is receiving this weighted input signal. It does the processing of that weighted input signal and then links it to the output variable. That is the typical structure that goes into a neural network. So neural networks, typically we are calling them as neurons, just to use the word brain related word terminology. So these are all different kinds of neurons. Each input is a different neuron, each output is a different neuron, the processing is happening through neuron. So they are typically the building blocks to construct the model. So in some cases we can also have some hidden neurons, where I'll talk about them in the next slide. So we'll have something called hidden neurons, which are actually used for building some complex models as well. So if I have to talk about some of the key characteristics of neural networks, every neural network will have an activation function. In detail, different types of activation functions I'm trying to bring up in the next slide. But basically the activation function, the job, as we have seen here, it is taking the neuron's net input signal. Net input signal is weighted, W1x1 plus W2x2 plus W3x3. So this is the weighted input signal that has been taken as an input. This activation function is taking it into an input and it converts it into a single output signal, and so it does some calculation on that input. We will see that what it does. It does some kind of a calculation on that input signal, and converts it into an output signal, and that output signal is broadcasted further into the network. So which means it could go to the next layer. So this whole weighted input signal, some kind of transformation occurs on that weighted input signal based on the activation function that I am supplying to it, and that transformed single value will go further in the network. That is what is the job of activation function. There are different types of activation functions. We'll talk about them. Then the other important characteristic of neural network is the architecture of the network, which in other words we call it as the topology of the network. So how many neurons are there? Right? We typically talk about three types of neurons: input neurons, output neurons, and hidden neurons. So we talk about how many neurons are there in the model, as well as how many layers are there. So all inputs, hidden layer 1, hidden layer 2, output. So mean there are 4 layers: input, hidden layer 1, hidden layer 2, output. Or I can talk about input, hidden layer, output. Or I can talk of input layer, output layer, no hidden layers at all. So these are the different kinds of network topologies I am talking of. Number of neurons that are there in each of the layers, along with that number of layers that are there, and how all these layers are connected. So the basic network diagram associated with inputs, hiddens and outputs is what we call as the network topology. That's one more characteristic of neural network that we need to understand. Then we are talking about the training algorithm. Basically, how am I coming out with W1, W2, W3? How the weights are typically set. So, what is the way in which the weights for each of these input signals is typically provided, so that some neurons get excited or some neurons get inhibited in proportion to the input signal. Based on the input signal, if I want to either inhibit a particular neuron or excite a particular neuron, what should be the kind of weights that I have to set for W1, W2, W3. So that goes as a part of the training algorithm. Again, we have different kinds of training algorithms that are there. So which the objective of the training algorithm is coming out with the optimal set of weights for each of the various input signals. So that's how the overall concept of the artificial neural network comes into picture. Alright. Then comes the next important concept, which is what we call as the activation functions. Now we have said there are three important things that we need to understand about the neural networks. One being the activation functions, two being the network topology or the architecture, and third one being the training algorithm. So when we are using the tools or technologies like R, these are the three things which I can really keep changing or play around with. So initially I can start off with one activation function, one type of topology and one type of training algorithm. And after that I can change them. I can see how the model is improving or worsening. So basically if I say when I am working with tools, I have the flexibility with respect to using my own activation function or different types of activation functions while modeling. I have the flexibility in changing the topology of the network. I have the flexibility in changing the training algorithm that is associated with the network. So first we talk about the activation function. So we said that the input signal comes to it in the form of W1 X1, W2 X2, W3 X3. So we are talking about a mechanism by which the neural network that we are talking of, it processes this information. So it will transform this particular signal into one single output signal. This weighted input signal is transformed into a single output signal and it is passed into the next layer in the network. So what is that mechanism that is being applied? So it is typically chosen based on the mathematical characteristics and the kind of relationships that are there between the input and the output. Very common function that is being used by majority of the training algorithms, by majority of the R programs that we look at. The most common activation function that is being used is a sigmoid function, where we are computing what is called as f of x, which is based on 1 by 1 plus e to the power of minus x. So the other way of looking at it is 1 by 1 plus 1 by e to the power of x, which actually becomes e to the power of x divided by e to the power of x plus 1. You will see that this value at any point in time will lie between 0 and 1 only. Right? It will lie between 0 and 1 only. But at the same time it is differentiable. Almost at every point I can have a derivative for this. For the entire range of input I can have a derivative. So the most common activation function where the data gets transformed is the sigmoid function. So the moment I am passing the input W1 X1 plus W2 X2 plus W3 X3 to it, depending on the weights whatever are decided. So this is called as X. Now this X will go as an input out here and an f of x is computed, which means the input is actually transformed by applying this kind of an activation function. The input is typically transformed and that transformed value will actually start passing on to the next layer in the neural network. But not necessary that every time I have to use only the sigmoid activation function. I could also use a linear function, but as we know the linear function is more or less like a linear regression itself. So we don't get too much of a difference when we are using a linear activation function. In some cases we talk about a saturated linear, means up to a certain range it is linear, but after that it flattens out to -1 or it flattens out at +1. So between -1 and +1 it is linear. Anything beyond 1 with positive or negative, it gets saturated at 1. So which means the range of this is -1 to 1, whereas the range of linear activation function is -infinity to infinity. Then I can also have hyperbolic tangent, which is tan h kind of an activation function. If you see, even this one will lie between -1 to +1. Just like a saturated linear, but you see that it is more and more a smooth curve which is differentiable across again. So this is another hyperbolic tangential function, right? You could see that the values wise for this a slight difference is existing. At 0 you could see that the y value is 0, whereas here if x is 0 the y is coming out to be 0.5. So we have a small difference between the two, but the shape wise you see that more or less the shapes are the same between the two functions. So when x equal to 0, here we are getting it as 0, y is 0, whereas here it is 0.5. Then we can also have a Gaussian activation function, which is more like a normally distributed, which means its range is between minus infinity to plus infinity. So these are the different kinds of transformations I can very well do on my x value. I can very well transform my x, which is a weighted input signal, into one of these forms. Though sigmoid is the most common form of activation function that is generally used. So as we have seen, the key difference is for some of them the output signal range is between 0 to 1. Especially in case of sigmoid, I see that the output range is between 0 to 1, whereas in case of saturated linear or even in case of hyperbolic tangent, you find that the range is between minus 1 to plus 1, and in case of Gaussian or linear, we find the output range to be between minus infinity to plus infinity. So that's the major difference across the different models. So the choice is typically based so that it fits some type of data more appropriately. Particularly if you see, if I have to use a linear activation function, if I want more or less similar to a linear regression model, it's better that I choose a linear activation function. But generally when I am looking at radial basis framework or a network, then I would be using a Gaussian activation function. So depending on the kind of data that I'm expecting, kind of relationship that I'm expecting, I'll use an appropriate activation function. Now, here we need to have an understanding of something else, which is called as quashing function. See, some functions that we are using, right, apart from these or even these, some functions that we are using, they squeeze the input values into a small range of outputs. Now you are seeing whatever are my W1 X1, W2 X2s, the whole thing will get reduced between 0 to 1. So if you look at the sigmoid function, whatever is the input value that I am giving to it, W1 X1, even X1 could be much bigger, X2 could be much bigger, but whatever are the inputs that I am giving to them, that whole output value will come between 0 to 1 only in case of a sigmoid, or minus 1 to plus 1 in case of a couple of other functions. So because the whole range is getting squashed, what we typically say is you transform to whatever extent possible, you transform all the inputs, let them not be in the original form. So which means you either normalize them, right? You can do a min-max kind of a normalization on that input data, or you can do a scaling, which is a z-score kind of normalization, but do some kind of a normalization so that all the values are somewhere in the range of 0, 1, very close to zeros itself. So you try to transform all the inputs so that the size impacts are completely removed, because anyhow it will transform it between 0 to 1. So just to make sure that the weights are not biased for one kind of variable compared to the other, what we talk about is we try to adjust all the variables in such a way that the sizes come around 0 itself. So either I do a standardization or a normalization using min-max normalization or a z-score normalization. So now the activation function, it takes the entire range. So now large values, otherwise if this transformation is not done or if this normalization is not done, there is a possibility that those features which are having large values, they might dominate those features where the values are very small. I don't want that kind of thing to happen. So we are bringing all the variables to a common scale, either between 0 to 1 or it's a Z scale where everything is transformed into the corresponding Z score. So by doing this, what happens is the training method becomes more and more faster. All kinds of input values, it can really skin through the different input values quite comfortably, and the training process becomes more and more faster. So this is what we need to understand regarding the activation function. Then comes the next aspect, which talks about the topology of the network. Otherwise, we are calling as the architecture of the network. So this talks about the patterns and the structure of all the neurons. So we have different input neurons, we have an output neuron, we might have different hidden neurons in different layers. So this is what we are calling as the pattern and the structure of the interconnected neuron. So depending on the structure, I can very well assess what is the complexity of the task which is doing the learning process. How much complex learning is occurring here. So if the network is very complex, there is an advantage, there is a disadvantage. One, it can do a very good pattern recognition. So it can identify the patterns much better. It can go with very detailed patterns analysis. It can bring out very detailed patterns. But at the same time, there is a possibility of overfitting as well. So we have to be very careful in terms of to how much complexity I want to make my model. And whenever we are talking about the topology of the network, we talk about how many layers are there. Is it only 2 layers where input and output, or 3 layers where one is a hidden layer, 4 layers, we have 2 hidden layers, and so on. So I have to specify how many layers are there in the network. So whether the information among the layers, so I am talking about layer 1, layer 2, layer 3. Whether the information flows only in the forward direction like this, or we also have a loop kind of thing in terms of the flow of the information. So is it possible that the information is traveling backwards in the layer? So that's the second thing that we are looking at. And within each layer, how many nodes are there? Is it 3 nodes, 5 nodes, 10 nodes? What is it? So whenever we talk about the topology, we have to talk about all these things. How many layers are there altogether? How many nodes are there in each of the layer? Is it possible that the information travels backwards within the network? So if I have to spend some time in terms of understanding each of these individual aspects, when I talk about the number of layers, the first thing, input nodes. So input nodes are the ones which are nothing but your input data. So you have input data, each input data becomes one input node. So it is receiving unprocessed signals directly from the input data. So whatever the number of input data we have, those many input nodes are forming in the network. Each input node is responsible for a single feature in the data set. So depending on number of variables that we have, number of input variables that we have in the model, those many input nodes are getting formed in the neural network. Similarly, I have output nodes. So output nodes are nothing but these are the ones that are receiving the signals from the input nodes. So basically we said that input nodes, there is a weighted average on the different input nodes values, and that weighted average is resulting in, or weighted sum is resulting in an activation function. This activation function will convert the signal, the input signal, and based on that, that activation function is coming out with a final prediction. So converting it into an output node. The signal for the output node is typically getting created out here. So the input and the output nodes are put in the form of layers. So input nodes are in one layer, the output is there in another layer. So if there is nothing intermediate where I am linking all of them directly together, then this is called as a single layer network. Only one set of connection weights, all inputs directly linked to the output. So these are called as linearly separable kind of pattern. So we are not bringing any kind of hidden layers out here. It's a straightforward stuff, a single layer network. So if I have to look at a typical single layer network, so let's say I have different input elements. So based on that, I am getting, let's say, three different input nodes. So I am calling x1, x2, x3. So x1 is one variable v1, v2, v3. So each input variable is corresponding to one input node. So there are some weights that we are giving to each of the input nodes, let's say W1, W2, W3. We are giving different weights to the input nodes, and this is becoming an output node Y. So there is an activation function that is applied out here and converted into a single output node. So this is what we are calling as a single layer network. Whereas there is a possibility that I can have a multiple layer network as well. So let's say I have different inputs x1, x2, x3. I'll have two hidden layers h1, h2, and let's say I have one output layer y. So these each data, each variable is corresponding to one input. Then it can very well be possible that each input is again linked with different hidden layers, and again each hidden layer I can link it with the output layer. So this kind of a network is typically called as a multi-layer network, where I have one or more hidden layers that are there as a part of the network. So you can have money, even in some cases you could also have H3, H4 as one more layer like this, and from there you could link it to the output. Then it is called as a multiple hidden layers are there in the network. So there could be multiple nodes hidden and multiple layers as well. So all these things typically come out as a part of the number of layers understanding. So multi-layer network. So there are one or more hidden layers. The signals from the input nodes are typically processed. Some kind of calculations are done at the hidden layer before they are transferred to the output node. So the whole network is fully connected. So all input nodes connected to all hidden nodes connected to all output nodes. That is the kind of network number of layers that we have to talk of in the network topology. Alright. So then the next important part that we have to look at here is the direction of the information travel. Is it that the information travels only in the forward direction, or is it possible that there is some level of looping kind of stuff, or the backward flow of information as well? So that's also the one more important aspect that we have to understand. So regarding this, again there are two major classifications that I can do with respect to the networks. One I call them as feed forward networks, and the second one is a feedback network. So when we talk about the feed forward networks, the input signal, so this is my input signal, it is fed continuously in one direction itself. So it goes from one layer to the other layer. So this is input layer, this is hidden layer, this is output layer. So it goes from only in the one direction. There is no backward movement of the input signal. Till the output layer, it's only in the forward direction. But the flexibility wise, I have number of layers, so I can have 3 layers, 4 layers. So that's how the different kinds of handlings can come in. So we can, so the when we are talking about the flexibility in this kind of a network, one, the flexibility I have with respect to how many levels I have to build, how many layers I have to build, how many nodes are there at each level, which means how many hidden nodes are required, 2, 3, 1, how many hidden nodes are there in each of the layers, and if there are multiple outcomes, how can I really model all those multiple outcomes, and if I require more number of hidden layers also. So all these are flexible, but whatever are the number of layers that I am talking of, whatever is the structure that I am talking of, the information moves only in the forward direction in case of feed forward networks. So they are generally applied to nowadays there are so many real world problems where these feed forward networks are more heavily applied. And one of probably if you are talking about the standard with respect to artificial neural networks today, we use a technique called multi-layer perceptron. So multi-layer perceptron is the most heavily used used kind of architecture today, which is again a part of feed forward network only. Whereas when it comes to feedback networks or recurrent networks, there is a possibility that the signal can travel, either it can loop here itself or it can travel very much backwards after some time, or it can loop with a time delay. Any of the things can very well happen. So the signal can travel in both the direction. So there is a looping that gets created in case of feedback networks. So if there is a complex pattern and learning has to happen based on a complex pattern, I can very well use the feedback networks. So especially if I am talking about a sequence of events over a period of time, right, especially for stock market predictions, weather forecastings, where I am talking about different sequence of events over a period of time, I can very well use the feedback networks. But what we really see is it makes the model very, very complex. So developing a real world application based on the feedback networks is very, very a complex task, right? But neural networks can very well be used from that perspective as well. Then the third important part in network topology is how many nodes are there in each of the layers. So input nodes predetermined, because depends on the number of input variables or features that are there in the input data. I am determining the number of input nodes. Coming to the number of output nodes depends on the number of outcomes. So how many dependent variables are there? Generally I have one single dependent variable. So I am giving my output nodes, the one single dependent variable is being provided. And if it is for classification purposes, right, if it is for a numerical purpose, yes, I have only one dependent variable. Whereas if I am talking about the classification purpose, probably I have many different classes of the dependent variable. So that's how I have to give it as output node. So number of class levels that are there in the outcome will become my output nodes. Then I can have number of hidden nodes. So they are completely decided by the analyst, the modeler. But before the going ahead with the model itself, training model itself, I have to decide on how many hidden nodes are to be taken. Though there is no ballpark kind of a rule, no kind of a formula which says how many neurons or how many nodes should be there in the hidden layer. So it's basically probably you can do the experimentation with different number of hidden layers and different number of nodes in each of the hidden layer, with the primary objective of what is the level of prediction accuracy that the model is able to generate. So how many I have to use generally is based on the number of input nodes, how much of training data I have, what is the size of the training data, how much of noisy data is there, how much of variation, how much of volatility is there as a part of your training data, and what is the level of complexity that could be existing with the training task. Though there is no such formula, based on the experience I can say I should go either with one hidden node or two or three or 10 or whatever it is. But we have to understand, if the network is becoming more and more complex, when will it become complex? One, if there are more hidden layers in it, and each hidden layer having more number of hidden nodes. In that case, the model is becoming more and more complex. So the number of network connections are growing and growing. That is what will make the model very complex. So the complex problems can be learned quite comfortably there. The modeling will be quite complex, but there is a lot of learning that can happen. But at the same time, the downside is there is a possibility of overfitting as well. So we have to balance between the two. More and more hidden layers might increase the possibility of solving a particular problem, but at the same time, there might be a possibility of overfitting the model to the data. So the large neural networks, if I have too much of complexity, they could be very, very computationally expensive, and because of that reason, the process might extremely slow down. So building such kind of a network will become very, very time consuming. So generally it is suggested that try to use as fewer number of nodes as possible, but the performance should be good enough. So you trade off. Try to have as minimum number of nodes as possible, but where the performance can very well be maximized. So it's a kind of an optimization thing that you have to get into while deciding how many nodes are appropriate in a particular network topology. Then the next aspect that we are looking at here is training the neural networks with a mechanism called back propagation. Especially when we are using the word back propagation, it is learning from the errors, learning from the mistakes. So that is what we are calling as back propagation. So as the neural network processes the input data, right, the connections between the neurons are either strengthened or weakened. Now this is where we are talking about different kinds of algorithms. So based on the processing of the input data, between the neurons which are there in the input layer, hidden layer, output layer, their connections can be either strengthened or weakened. Now whatever it is, the errors that come out, once I have done the first layer analysis, I have built some kind of W1, W2, W3 as the weights, and based on the weights I have transformed this input signal into a hidden layer. The hidden layer gets transformed into an output. Now based on this, I have tried applying this model back to my training data. When I apply the same model to the training data, there are errors that are coming. So I am actually transferring the errors back into the model. I am trying to improvise my model by learning from the errors that are coming from the existing, which means I am now changing the weights in such a way that the error is coming down and down and down. So it's more and more of an iterative process, right? So that kind of a mechanism where we are learning from the errors is what is called as a back propagation. So it's a strategy of back propagating the errors. So because it's a kind of an iterative process, it's very, very slow compared to many other machine learning algorithms. So even if my network is a multi-layer feed forward network, so the information is a feed forward only. From input it is going to hidden, it's going to output. But whatever the errors that are coming up, they are again back propagated. The model is improvised. So generally the most common one we are looking at nowadays is a multi-layer feed-forward network along with a back propagation kind of an algorithm. So we could use these kind of algorithms for the classification as well as numerical prediction problems. They are probably one of the most accurate kind of approaches. And the biggest advantage is they don't make any kind of assumptions regarding the data and even the relationships. So there is no need that the data has to be normal. Whereas my regression model typically assumes that my dependent variable is more or less normally distributed. So regarding the data or the kind of distributions associated with the data or the relationships, there are no assumptions that are being made by the neural networks. But of course, as we have been discussing, there is a very heavy computation that goes into it, and because of a lot of iterative process, the process gets very slowed down. So the training process is taking too long time. So if the network topology is getting very complex, you will find that the learning that is being done by the neural networks is very slow. While at the same time, if the architecture is very complex, there is even a possibility that the model is very much prone to being overfit as well. And as we have already talked about, if I have to really explain the model to someone else, or probably talk about how do I, which variables are influencing the dependent variable heavily, which of them are not influencing, I cannot make any kind of individualistic interpretation that easily. The interpretability of the model is very difficult. Whereas in case of a simple linear regression or a multiple linear regression kind of a model, I can very well explain which are the significant variables, which are insignificant variables, etc. But here it's a kind of a black box model. The interpretations become very difficult. But of course, sometimes we have to take it as it is, because we are able to, if it can result in a better prediction accuracy, we can very well go ahead with the usage of the neural networks quite comfortably. So with this, I want to take up a data set, try looking at, along with neural networks, I also want to look at using the other mechanisms also, to see in each of the cases which one is doing a better job in terms of predicting the dependent variable in relationship with the various independent or explanatory variables. So we'll get started with the data and we'll try to apply all the various processes on that particular data. Alright. Alright, so let's start looking at the data. Now I am taking the insurance data that I have stored in this location on my system. So I'm taking it into a variable called insurance, which is done through read.csv. So I'm looking at first few quick things which we do in any kind of the process. Okay, but before I go into it, let me just do a couple of more things conceptually. So each iteration of a back propagation algorithm, so once the error comes out, that error is again taken back as an input, the weights are changed again. So that kind of an iteration is called as epoch. So many cycles, this process keeps continuing. So initially the weights are set in a random way, but based on the kind of errors that are coming out, the weights are typically adjusted. So that's a kind of a cycle through which the overall process flows. And there is a stopping criteria, right? So algorithm is cycling through the process. So this is where we talk about different kinds of algorithms. In R, we will be seeing when we are applying the neural networks, right? We talk about prop plus, we talk about prop minus, we talk about SLR. So these are the different kinds of algorithms that we would be using. So until the final layer is reached, and the error part is completely reduced. So this process keeps continuing. So that is what we would be seeing when we are doing it as a part of our data. So let's get started with the data. The step one, we have collected it. Then we'll try to do some basic exploration of the data, whatever is the method that we are using. I can look at the structure of the data. So I'll use the structure of insurance. So which says there are 1338 observations altogether, 7 variables are there, right? Age is an integer, sex is a factor with 2 levels, BMI is a numeric, children it's an integer, smoker yes or no, factor with 2 levels, region to what region the person belongs to, it's a factor with 4 levels, and the charges we are talking of what is the insurance charges that are typically incurred by the person. So these are some of the variables that we have. Now my objective here is take these charges as a dependent variable and all others as the independent variables and go ahead building the model. So initially I want to build it as a linear regression model. So I'll just quickly use all of them. So I require a linear regression model first. Then I will build a regression tree which comes from this rpart package and rpart function. Then also I would be building a model tree from this m5p function. So I want to use all these three functions. So m5p is there as a part of rveka package. rpart is there as a part of rpart package itself, and this is a basic R itself. I don't want to go in detail because we have already dealt with all these algorithms in our previous sessions. So here I want to just do a comparative analysis. So I'll build the model on a training data, test it on a testing data, and see what is the level of accuracy the model is generating. So to do that, initially I require the training data and the testing data. So approximately 70% of the data I can make it as a training data. So almost 937. So I'll take 937 records as a part of training data, which will leave the remaining 1338 minus 936, which is almost 401. So 401 will be there as a part of the test data. So we'll set that. We'll initially set a seed value, let's say 1000. Then I am taking a variable called train, which is selecting 937 observations, which is picking 937 numbers randomly from 1 to 1338. So for that I'll use a sample function saying within the numbers 1 to 1338, pick up 937 observations where the replacement is false. So no repetition at all. So that's how you get your train. And based on that you get your training data, which is nothing but it's a subset of your insurance. It's a subset of your insurance where you are taking the train rows which are there, which have come through the random sample. So only those numbers which are there as a part of the train we would include for the training data. So that's how we take a subset of the overall insurance data frame and assign it to train data. Similarly, I'll take the test data where I am taking the other subset, which means anything that does not contain the train. So minus train, comma blank. I am taking all the columns, but those rows which do not contain the train. Train is a random 937 observations pulled from 1 to 1338. So this is how I am getting my training data and the testing data. Then I can go ahead building the model. So what I'll do is model underscore linear regression. Right, let me call it model underscore LR, wherein I'm building a linear regression model. So in the linear regression model, I have to give the dependent variable, which is charges. I'm not looking at the normality and all that stuff. Taking the data as it is, I'm trying to see what each of the models are typically giving. So I'm doing charges as a dependent variable. All others I take an independent variable, so that's where I'm taking a dot. Dot means all the other variables I'm taking as independent variables. Then the other input I have to give is data. So the data that I am having here is the train data. I am doing the training based on the train data. So that's how I have built my linear regression model. Right, this is my linear regression model. When I type the name of the model, I get my model altogether. So where it gives me the different coefficients associated with the model. So minus 11,693 plus 252.2 times age plus 148.1 times the sex, whether if it is a male, etc. etc. Similarly, I can get much more detailed report regarding that particular model by giving a summary of that particular model. Right, I don't want to explain it in depth because we had dealt a separate session for the linear regression. So here it has given that these are the coefficients. Probably the gender is insignificant here, the p-value greater than 0.05, and it looks like region northwest is also insignificant, whereas all others are significant in some form or the other. But some of the important things, let's make a note out here. The R squared of the model is 73.81, right? So when I have taken linear regression, it came out that the R squared of the model is 73.81%. But remember that it is on the training data. I will do the same on the testing data, and after that I will give a confirmation. But right now on the training data, it has come out that the R squared is 73.81 and the standard error is coming out to 6,284. These are two important things. On the training data, my R squared has come out to around 73.81%. But we can apply this model on the testing data. So that's where I'll call it as P underscore LR, which is my predicted values on the testing data. I'll use a function called predict, where I'll use my model. Model is model underscore LR, and the data that I am giving is test data. So based on this, the prediction is occurring. So the predicted values have typically come out. Now I want to find out the R squared associated with the predicted values using the linear regression model. So what comes out, my R squared is nothing but I'll take the correlation between the predicted value, which is P underscore LR, and the actual values, which are test data dollar charges. These are the actual values. So I'm taking the correlation between the two, but I'm taking the square of the correlation because I want R squared. So this is the R squared on the test data that I'm getting, which works out to 78.22%. So this is my accuracy of the model. If I'm using the linear regression, it worked out that the accuracy of the model is approximately 78.22%. Now, for the same data, same training data, same testing data, I want to go ahead and use a regression tree now. Right, we'll use neural networks as well. Of course, I'm not doing any kind of versionings or modifications here. In linear regression, again, I can improvise the model by doing some kind of transformations on the dependent variable, etc. But here I am not doing any such kind of things. I'm just using the data as it is, seeing what is the level of accuracy that each of the different models are typically giving up. So the same thing. Now I'll do the regression tree. So I'll install the package rpart for this. So I'll install the package rpart here. Oh, I think it might have already been installed on my system. So let me just load it. That should be sufficient because we have dealt it as a part of the other session. So yeah, rpart is already there on my system. So I'll build another model which is called as model underscore regression tree. RT I am calling it. rpart is the name of the function that I am using. Right, rpart is the name of the function. The dependent variable and the independent variable are similar. So I have to give charges as the dependent variable. Dot I will give as the independent variable. The data in this case I am trying to give, if I have to give the data, it is train data. So train data is the data that I am giving as an input to the model RT, which is a regression tree model. And if I have to check what is there as a part of the model RT, how did the model build it? So I am typing it model underscore RT. So it has given me that this is how it has broken it down. Or probably if I want to look at the graphical presentation of it, I can very well load rpart.plot package. Right, it can do even the graphical representation of the same. So we have loaded the rpart.plot package, and I can very well use rpart.plot, wherein I can give this model underscore RT as the input. So the graph that is generated is more like this. Right, I could very well see smoker equal to no. So that's one input that it is taken. And after that, for those people who are non-smokers, it is looking at age less than 42 or age greater than 42. Similarly, for those people who are not non-smokers, which means who are smokers, where their overall data there is 21% of it, it has classified based on the BMI. So some of them falling into 10, so 10%, 11%, and based on that their insurance charges are estimated. So overall there are only 4 branches, 4 leaves. So for each of the 4 leaves the insurance charges has come out like this. So for this group the insurance charges are only 5,500, which is an average of all the 415 people who have fallen into that group. Whereas for this group it came out to 12,341 for those people whose age is greater than or equal to 42.5 and they are smokers. They are not smokers. Their charges are average charges are 12,341. But for those people who are smokers but their BMI is less than 30.01, their charges are predicted as 21,000, but for those whose BMI is greater than 30, it has been predicted as 41. So that's how the regression tree model has done the prediction for us. Now, based on that, if I want to test it, so I'll call P underscore RT, right? If I want to really predict for a test data based on this model, I'm using predict, wherein I'm giving the model as model underscore RT, and I'm giving the same test data as the input. So this is what the model has given. Now I can very well find out the correlation between P underscore RT, whatever has been predicted by my regression tree model, along with the actual, which is test data dollar charges. So these are the correlation I am looking between these two, but I want R squared, so I'll take the square of it. So this is working out that for the same, if I am building a regression tree, it's working out that the R squared of the testing model is around 85.15%. So probably this model has done a slightly better job compared to your linear regression model in terms of predicting the testing data. So the R squared of the model looked slightly more higher. From 78 it went up to 85. So the model accuracy has gone up, which means the standard error of the prediction has actually gone down, which is also an indication that the range in which my predicted values are going to lie would be in a very, very narrower range. Now the same thing I would like to implement using a model tree. So for the model tree, I have to load RVK package, right? RVK package is what I'm loading. Again the same logic. I have M5P as the name of the function out here. So let me call it as model underscore model tree, where I am using M5P as the name of the package, wherein again I am giving the dependent variable, which is charges, tilde, independent variable, which are dot, and the data that I am giving to it is train data. So again the similar kind of a model is being built using the M5P function, which is taking care of a model tree. You see, it takes some time, but of course the tree got built. Now let's see what is being given by this model tree. Now you could see here, even when it comes to splitting the tree, more or less the process is the same. Smoker yes, smoker no. Then it has talked about age less than or equal to 42.5, age greater than 42.5. Similarly, for those smokers who are yes, it has looked at the BMI less than 30.01, greater than 30.01. Look like more or less the groups that were split, it looked more or less similar. But now what we could see is there is a separate formula. If you see LM for the first one, which is this particular leaf node, this is the formula that is linking the charges with the various independent variables that are existing. And the same logic continued, right? You could see for if it is number 2, which is this particular branch, for those people who are non-smokers but whose age is more than 42.5, this is how the charges are determined. Now what I could clearly see is here the weightages are slightly higher. So for smoker here the weightage is 43.473. Here also it is 473. The smoker did not change much. And if you see, the regions had a big difference here versus here. Whereas age wise, for smaller ages, the multiplier of age is only 135, whereas for larger ages, the multiplier for age is 374, which is also indicating that after 42.5, probably the charges are going at a much higher rate with respect to age. So whereas in a linear regression, I can get only one single coefficient per age. Whereas here I am getting different kinds of coefficients per age. The same logic, if you see BMI, here the BMI contribution is much lesser, the coordinates associated with the BMI. Whereas here you could see, for those people whose BMI is less than 30.01, the multiplier is 598. Whereas for those who are greater than 30.01, the multiplier became 616. So again, the BMI is different for different sets of people, and because they are smokers, you could see that the multiplier for the smoker is much higher here, 1674, whereas here it was only 473. So that's where you see different formulas coming up for each of the 4 leaf nodes. But yes, whatever are the, so if there are n number of leaf nodes, we'll get n such kind of formulas depicting the relationships between the dependent variable and the set of independent variables. Now, we will do the prediction p underscore model t mt. So we'll do a predict model underscore mt is the name of my model, and test data. I am applying this on my test data. So I have got the prediction. Now I can very well go ahead in terms of doing the correlation on my test data, which comes out as p underscore mt and test data dollar charges square. Now in this case, I am getting a correlation of R squared of 88.87%. So if I am looking at for this kind of a data, for this kind of an objective, my model is able to generate 88.87 kind of accuracy compared to a linear regression model which was operating at 78, or a regression tree model which was operating at 85. So now I want to see with the similar kind of a stuff, to what extent I could see the neural network improvise the process. So with respect to the neural network, if I have to work, few things that I have to make changes before I use the model. One, the data needs to be scaled, right? So I can use either a normalize or a scale, either a min-max normalization, or directly use the scale function which will do the z-score computation. Any transformation applied to the data prior to training of the model will be applied in the reverse at a later point, so that the whole data comes back into the original units itself. So we have to do the transformation right now. So for doing that transformation, what I would really like to look at is, whatever is the transformation that we are using, we'll do a simple scaling. But if there are categorical variables, we have to convert them into dummies. So what I can very well do is, for those variables which are having only 2 categories, let me again do the structure of insurance. So you see, sex is having only 2 levels. So I can treat it as dummy. So I'll convert it, right? Probably if required, I will set it like, so I'll call it insurance 1, wherein first I am taking only those variables which are already numbers. So I'll take it as insurance, right? Or probably first let me do it on this itself. So let me add insurance dollar, let me take the whole thing, insurance 1. Let me create one more variable wherein I am taking the whole insurance as a part of insurance 1. Now on this insurance 1, I will add another variable called male. wherein I am saying if else insurance $1 sex is equal to male, right? If this is equal to male, I will set this as 1, otherwise I'll set it as 0. So I'm getting one new column calling insurance $1 male. So I am making this also into a number rather than a factor. Similarly, I can do the same for smoker. Insurance $smoker. I'll set it if else insurance $1 smoker is equal to S. Instead of male, I'll set it to S. And all those who has S, it will be taken as 1, otherwise I'll take it as 0. But here for the region, I have to work it out. So I'll say insurance $1 northeast, right? I'll say insurance $northeast. So I have to set insurance 1 northeast, insurance 1, I am setting it as region. Within this region, I am trying to compare it with the word northeast. Okay, so then it is 1, otherwise it's 0, a dummy coding. Similarly, I have to do it with northwest as well. So I am calling insurance $1 northwest. Here also I am changing it to northwest. Then I can also use southeast. So I'll use southeast as one more. So I'm using it southeast, where the region I am setting it as southeast. So these are the dummy variables that I have created. So now when you are looking at the structure of insurance 1, yeah, it has come out that sex is still a factor because anyhow we have converted it into a number with 0 and 1. So probably I can remove this sex from this data, and I can also remove the region from this data. So I could very well say that I don't want the second column as well as the sixth column from the data. So I'll say insurance 1 is nothing but insurance 1, a subset of it, where I am taking all the rows, whereas in the columns I'll say minus of 2, 6. I'll set it as minus of 2, 6. So if you look at now the structure of insurance 1, it will be there without the column numbers 2 and 6. So there are only 9 columns out there. All of them are numbers, are integers. Now I have to do a transformation. For simplicity, let me do the scale function directly. So I'll call it as insurance 2, or probably insurance underscore Z score, right? And insurance 1 underscore Z, which I am calling it directly using the scale function. So I'll take the scale of insurance 1 directly. That's it. So now if you see the The head of insurance 1 underscore Z, where you are observing the first few values of insurance 1. So all of them are somewhere around zeros itself. We have different kinds of values associated with each of the male, female, genders, and the regions, the charges, the smokers, children, BMI, etc. So now I have now I'll from this I'll make my training data and testing data, right? So obviously we already have it. The only thing is now I'll take it as the train data. I'll simply take it as insurance 1 underscore Z. Out of this I am taking the train comma blank as my training data, and similarly when I am calling it as test data, I am taking it as insurance 1 underscore Z. I am taking those rows which are not there as a part of the train, so I am taking it as minus train comma blank. So I have broken the data, split the data into a training data as well as the testing data out here. So the scaling of the data is very much performed. Now it's time for me to apply the neural network to train the model. So we are talking about a multi-layer. We are bringing in multi-layers, means we have input layer, hidden layer as well as the output layer. I can have one hidden layer or more hidden layers, or even within the one single hidden layer I can talk about different kinds of hidden nodes. So we are bringing in a multi-layer feed forward neural network. So there is no feed backwards or recurrent network. We can implement that using a neural net package. So we can very well install the neural net package. So it would have been already installed on my system. So let me simply load the neural net, right? Otherwise you have to install the neural net. Now here it is already installed. So I am simply loading the neural net package. Then again the model is nothing but I am using neural net as a function, dependent variable, tilde the predictors. The only thing here, I can't use the dot notation here. I have to give the list of all the variables. So let me do model underscore NN neural network. I'm using neural net as a function. The dependent variable for me is charges, tilde. I'm giving a list of all the independent variables. So I'm giving age plus BMI plus children plus smoker plus male plus northeast plus northwest plus southeast. So these are the different independent variables that are there as a part of the model. If there are some interactions also I can provide them. Then I have to give my data. The data in this case is nothing but my train data. So I am giving a train data, and I have to give the hidden layers or hidden nodes. How many hidden nodes are there in the typical model? So let me set by default the hidden is equal to 1. I can set the hidden is equal to 1. That's also a default thing. But after that I can very well improvise the model. So let me first build the initial version of the model. Now it's taking some kind of a time to build the model. That is where we said the learning process is slightly slower. Right? It specifies the input, takes the target, which is the dependent variable. Then we have the set of predictors, the data, and finally I am getting the model. So we got the model out here. So if I really want to check out what is there as a part of the model, I can very well type the name of the model. So I'll type it as model underscore NN. So it is simply saying it did one repetition only. The whole process was repeated only once. So the error in the model is around 106. This is the threshold that it has reached. It has taken almost 65,744 steps to come towards that. And now if I really want a plot of the model, I can very well say plot model NN. So if I want to plot it, this is how the model is typically coming up. So there is one input node for each of the features. For each of the features there is one input node. Then we have one single hidden layer, hidden node and a hidden layer, one hidden layer and which has one hidden node, and we have the output part, right? And these are the weights that are associated with each one of them. The weights are done as a part of the training algorithm that came out in a way that the overall error is typically minimized. So in this plot you could see how many steps that it has taken to train the model, and we are also talking about sum of squared errors. So especially we would be using it when we are evaluating the performance of the model. So probably from one hidden layer, if I am changing it to two hidden layers or two hidden nodes or three hidden nodes, then probably comparing the error that is coming out of each one of them would be more and more handy for us, right? So that is how the basic neural network model gets built. So we have visualized the network topology also using the plot function. Now, again I have to do the prediction of this model on the test data, right, to really assess what is the goodness, because here I can't understand what is minus 0.33, I can't say what is minus 0.4. It's very difficult for me to understand this because there is a lot of transformation and all that I have gotten out here. If you look at just typing out question mark neural net to really see what this model can do, what this function can do, we are taking the help of it, wherein we are able to understand that it is used to train neural networks using back propagation. So only when we are when our objective is involving back propagation, which means the errors that are coming out, they are taken as the input to improvise the model. So resilient back propagation goes with rprop, with or without backtracking. So when we say rprop plus, it is called as resilient back propagation with backtracking, or we have resilient back propagation without backtracking. So it is directly training the neural networks by going with this kind of a mechanism. So we have some kind of custom choices. Error functions, we can have a custom choice. Activation function, we can have custom choice. Now you could see here, if we are looking at the overall formula, okay, this is the formula which is dependent variable till the independent variable. I am giving the data. I have to specify how many hidden neurons are there in each of the layers. So if I have two layers, I have to put it as a C function, C1, 2, C2, 5. So I have to give different kinds of hidden neurons in each of the layers out here. Then the stopping criteria is coming through a threshold. This I don't need to generally look at. Then step max is talking of how many steps. Earlier we have got that it has taken almost 6,000 steps or something. So what is the maximum number of steps? Generally it stops after 100,000 steps. But in some cases if I want to increase this number, I can very well increase it. But more than that, if I don't give any start weights, then probably the randomly the system will generate and it will go ahead. But more importantly here, the algorithm. Here it is saying RPROP plus. The algorithm is nothing but what is the kind of algorithm, that training algorithm that I have to give to calculate the neural network. So here 4 or 5 kind of algorithms are typically supplemented by this particular function, supported. When you say backprop, so it's a back propagation algorithm. When you say rprop plus or rprop minus, we are talking about back propagation with backtracking or without backtracking kind of stuff. And when you are talking about SAG, we are talking about globally convergent algorithm, and SLR is talking about the slowest learning rate kind. So we have 5 different things that we can change. So the default is it uses rprop plus, which is resilient propagation with backtracking. So we can very well change that if we really want it. Then the error function also we can change, right? You could see here the default error is sum of squared errors, SSE. But otherwise I can also set it to CE, which is nothing but cross entropy, which is generally, if I want it for class predictions, then it's better. For the classification data, it's better that I use class entropy. Whereas for numerical predictions, it's better that I use sum of squared errors. Though it's not that mandatory, because at the end I have transformed all these things. Then we are talking about an activation function. So by default it is logistic, but I can also set hyperbolic tangent, where I can set it to tan h. So these are the 2 different kinds of activation functions that are typically supported. Now all this is what typically can be done through your neural net kind of a function. Okay, so let's go back. So that has created the model, the neural net as a function. So now you know, if you really want to make some kind of changes to the model, what are the different kinds of changes that you can typically do. Now we can do the prediction. So P underscore NN is the predicted value I am taking. But let's see here, we are not using the predict function out here. Predict function is not defined for neural network kind of an object. So we will use compute function here. So we will say predict compute model and the test data. But of course, let me tell you here, for compute, the test data does not require, I should not give the output variable in the test data. Only the input variables need to be given. So I know that the 5th variable is the output variable. So I would not give the 5th variable as an input to this compute function. So I will say compute, wherein the model that I am taking is model underscore NN, and the test data that I am taking is test data, wherein I am taking all the rows but not the 5th column, all the columns except the 5th column. So I am taking that as a test data and giving as an input to my P underscore NN. So there is a kind of a prediction that is already done. Now I will try to find out the correlation or the R squared between P underscore NN comma test data dollar charges, and I'll take the square of it, which is giving me, okay, so P underscore NN, okay, P underscore NN is my test data or is my predicted. But what you see is the predicted values here, it returns 2 things. One is it returns neurons, So for each layer in the network, it will store the neurons. So what neurons are there in the hidden layer, what are there in the output layer, etc. But this particular output, $net dot result, this is the one that is containing the predicted value. So when I am doing a correlation, I can't just do $NN, but I'll have to take it as $NN net dot result, because net dot result is the one that is storing the predicted values. So let me see what has happened to P.NN. Net dot result. So I am trying to find the correlation between P.NN, P underscore NN $net dot result and test data. I am trying to find the correlation. Let me see what is coming out with P underscore NN $net dot result. So it's coming out like this. So I can find out the class of so it's a matrix. So it's better that I convert it. Now if I look at the class of test data $charges, what is the class of this? Okay, this is where there is some problem with the test data $charges. What is happening with the test data $charges? So let me look at the test data, structure of test data. If I see, train data. If I look at structure of train data, head of train data. So this is what is coming out as the head of train data. And if I am looking at the head of test data, so this is what is coming out as the head of test data. Okay, so test data, dim of test data, if I am doing 401 rows, 9 columns. Dim of P underscore NN, okay, P underscore NN $net dot result, 401 rows, 1 column. So I should be able to do the correlation between and you look at test data where I am taking the rows, all rows and the fifth column. Okay, so now I can take the square of it. So which is giving me 80.31%. So if I'm going with this model, I got R squared value of 80.31% going with one hidden neuron in the model. But now I want to improvise the model by increasing the number of hidden neurons. So let me see, if I increase the number of hidden neurons, what is the kind of change that is coming to the model. Instead of 1, let's say let me make the hidden neurons to 3. So a new model is getting created now. Everything else is remaining the same. I have just increased the number of hidden neurons as 3. So with these 3 hidden neurons, again I can do the same process. So first it's taking some time to build the model itself. So let it complete the model building. Now if I want to plot this model, I'll find that there are 3 layers in this particular model. So hidden layers. So now you see that the model is becoming so complex. It took 57,000 steps, but the error has come down drastically. From 106 earlier, now the error has come to 66. So this is what I could see. If I am increasing the complexity of the model, there is a chance that the learning is more and more improvised, which can result in the learning being much comfortable on the training data, but at the same time the overfitting also is very much possible. Now I can do the computation again, right? So I can very well talk about P underscore NN now, where again I'll do the prediction. So let me do the P underscore NN, which is doing the prediction. Where we are doing the computing of the model on the test data. So we got the model, the predicted values we have got. Now I can go ahead in terms of finding the correlation squared, because the P dot NN has been applied. Now I'll take the R squared between the predicted values and the actual values. Now this is showing 89.06 with 3 hidden layers. I could see that the correlation has come out, the R squared has come out to 89.06. Whereas when we have used the model trees earlier, the accuracy came to 88.87. But now I could see the accuracy has touched 89.06. Now the same way, probably if I improvise, let me try improvising the model now by bringing in 5 hidden layers, nothing else. So the model training process is taking a lot of time. But let's see if the accuracy is improving heavily or not when we are working on the testing data. But now when I do the plot, probably it's the most confusing plot we can think of. Very complex plot that got created. But once the plot is created, let's say now I am doing the prediction. So the prediction is taken care of, and now I can go ahead in terms of finding the correlation squared. Now this says it is only 86.97. So what you could see is by increasing it to 5 different hidden nodes, in fact the accuracy has come down, the R squared has come down, because there might have been a lot of overfitting on the training data, right? Probably if we plot it also, we could see that the error is still 66 here. Even in the earlier case it was 66, so there is no decrease in the error at all. So this is how we can iterate the process, and in some cases now we have changed here only the number of hidden nodes. but we can very well change the algorithm itself. Here we are talking about rprop plus algorithm, but I could have tried with no backtracking, rprop minus, or I could have used SLR algorithm or SAG kind of an algorithm to finally look out for which one is giving a much better prediction with the test data, much better accuracy with the test data. So here we are measuring the correlation between the predicted and the true value. Correlation or the square of it, which is the r squared. So the more and more closer it is to 1, we say that the relationship is very strong. Otherwise it can result in much weaker and weaker kind of relationships. So that's how we can work out. We can change the topologies, we can increase the hidden layers. All these kinds of things can very well be played around to finally come out with a much better model which can do the predictions on our data quite comfortably. So that's how we have to understand the overall process. So we have to keep on checking whether the R squared is getting improved. So we can change one, the activation functions. At least in this function, neural net, we have two activation functions. One I can give it as tan h, which is an hyperbolic tangent, and two, which is the default one itself, which is the logistic, which is going with the sigmoid function itself. So these two are the activation functions that I can play around with. The network topology I can change by giving the hidden nodes and even the hidden layers that I want. So depending on how many nodes I want in each of the hidden layers, I can change that. And I can also change my training algorithm. There are 4-5 algorithms that are supported: rprop plus, rprop minus, SLR, SAG, which is a global algorithm, and finally backprop. So we can very well use different kinds of names in the algorithm where we get different kinds of combinations. So I can try all these things, and based on that I can very well test them out on my test data, look at the R squared, and whichever is the one that is giving me a much higher R squared would be chosen for the futuristic prediction purposes. Alright. So that's how I want you to look at neural networks. I did not get into the heavier mathematical aspects of it. But yes, what a neural network typically does, how we can use for the prediction purposes, what are the various attributes that you can play around with when you are working with neural networks on a data. So these are some of the things I want you to have a good understanding of so that you can play around with those flexible aspects, change the inputs, change the input arguments in the formula, and see how the model is improvising or worsening the prediction part. Test it with your R squared on the test data, and finally use an appropriate model for the prediction purposes. I hope you got a good amount of understanding on the usage of neural networks for the prediction purpose. If you have any further queries, you can very well get back to me by giving me a call on the number that I have provided below, or you can send in an email at the email address that I have highlighted at the bottom. Thanks a lot for listening to this session. Thank you very much.